Okay, I figured out what the problem was with the notes, is that you guys had the right notes, and I was lecturing off of the AP calculus class version of the notes, which a lot of it is the same, but in your notes there were a few extra examples that I threw in just to help reinforce. So if you want to go back a couple slides on your note pages, I will fill those in for you. So I'm going to go back to this one, which was a proof for continuity. So this was just another opportunity for us to practice the 1, 2, 3 steps of proving continuity. And so a question might be posed to you something like, prove continuity at x is 2. And so if you were asked to do that, then you would set up the 3 steps and you'd approach 2 from the left. You'd approach 2 from the right, and then you would also check the actual value of f of 2. So looking at 2 from the left, that one's heading down and approaching the closed circle at -2. If we're approaching 2 from the right, we're also heading down, but we're approaching the open circle at a value of 0. That's an automatic failure in the first 2 steps. And so we would conclude that since step 1, which is the limit as x approaches 2 from the left, is not equal to the limit approaching 2 from the right, since that's the case, then f of x is discontinuous at x is 2. Now the next 2 examples are drawing your own as an understanding of what that's going to look like. So we are told to sketch a graph where this is true, where g of -1 equals 2. Now that's a physical point on the graph. So I'm going to go to -1, +2, and I'm going to put that physical point right there. And then we are told, however, that the limit does not exist. So when I'm told that the limit does not exist, so either limit, okay, so we've got either the limit approaching, let's see, the limit approaching from the left doesn't exist, or the limit approaching from the right doesn't exist, or they don't match, or there's a problem. And so all you need to do is draw some kind of gap discontinuity. So I could do maybe a nice parabola with an arrow going down there, and then I could do an open, and I could go up. There we go. Now the point exists, but the limit does not, because the left and the right aren't equal. So that could be a sample of how it could go. Someone else may have drawn it differently. Let's see, other options we could have would be where we totally miss that point altogether. We could have a graph that comes up and has an open circle and then goes beyond. Okay, now would that work? No, this does not work because this limit exists in this one. The left and the right hand are approaching the same number even though the spot is off. So this would not necessarily work. I have to have some kind of a gap or a discontinuity. Okay, so I could maybe have my gap like this. Now I have a big gap and a removable, so that would work for this one. Okay, some kind of gap. So if the limit does not exist, that means you got to draw a gap or a jump discontinuity. So now we sketch a graph where a point physically exists. So this is a physical point. It doesn't tell us where it is, but there's a physical point. And a limit exists, so that means there's no gap, but there's still a discontinuity. So if there's a physical point but there's no gap, that must mean that there was a removable. discontinuity. So I could draw something like this down to 0, put an open circle, and then keep going, and then put my physical points somewhere else. That would be a sample. Okay, the physical point exists. The limit also exists. There's no gap, but there's still a discontinuity. So this is describing a removable discontinuity situation. There's lots of ways you can create this as well. You can create really however you want as long as you're showing a removable discontinuity. So I could have an upside down parabola, and I could have the removable discontinuity sitting at the origin. That might be another sample. All right, so that finishes up 1.3a. 1.3b, we'll just move on. We're going to learn about continuous functions and their properties, and these functions are just going to be the building block on which we're going to move on to get into some real actual calculus stuff next week. So remember, the proof for the continuity, those 3 steps that we just reviewed. Okay, the third step is often the most forgotten, but it is the most essential because it's what makes the difference between just a limit and a continuous function. You can pass steps 1 and 2 and have a limit, but unless you can pass step 3 as well, you will not explicitly be a continuous function. So here's a question where there's a missing part. It's a piecewise function, but the a value is missing. And we need to make the function continuous. So that means we need to make all 3 steps match. So let's set up all 3 steps. Step 1, the limit approaching 1 from the left. Step 2, the limit approaching 1 from the right. And step 3, f of 1 itself. All right, let's go back to step 1. When we approach 1 from the left, we'll be using x squared minus a. And so that would be 1 minus squared minus a. 1 minus squared is still 1 minus, but when you're doing continuity, you can just put the whole number. You don't have to really stress about the plus or the minus, the left or the right. And so it's just 1 minus a. For step 2, when we're doing our limit from the right, we'll be using x plus 3. And so we'll put 1 plus into there and we'll add 3. That'll give me 4 plus, or just 4. And then when I'm doing f of 1 exactly, I just plug it right in and I get 4. All right, so we need to make sure that all of these things match. So basically we're coming down to the point these 2 things need to be set equal to each other. So I'm going to take 1 minus a and set it equal to 4, and then I'm going to subtract 1 from both sides, so negative a equals 3, so a must equal positive 3. So if a was positive 3, if a was negative 3, then this function would be continuous and all 3 steps would match. Here's another question. Find the values of a and b that would make the function continuous again. All right, well, we'll set up our 3 steps. So step 1, the limit as x approaches, this time negative 2 from the left. Step 2, the limit approaching negative 2 from the right. And f of negative 2 altogether. And you know what, there's a typo. I'm just noticing there should be a negative sign right there. All right, when we approach negative 2 from the left, we'll be using the equation x squared plus ax. So we'll put negative 2 in there. That would be negative 2 left squared plus a times negative 2 left. Negative 2 squared is positive 4, and it's technically 4 plus, but you don't have to worry about the pluses and the minuses, and then minus 2a. All right, when I am using negative 2 plus, I'll be using the equation 8 minus x. So that would be 8 minus negative 2, or 8 plus 2. Again, you can drop the plus or minus, and that's 10. So we know that step 1 and 2 need to match. Step 3, f of negative 2, well, that's just b. So let's make steps 1 and 2 match, and then we'll move on to make steps 2 and 3 match. So we want these two, 4 minus 2a, which is the first step, be set equal to 10. So I'll subtract 4 from both sides. So negative 2a is 6, and a is negative 3. I also need to make steps 2 and 3 match. So 10 for step 2 needs to be equal to b. And so we've got our answers where 10 is equal to b and negative 3 is equal to a. And that will make the function continuous. So again, we want to review, how do you identify if there's going to be a discontinuity? How could you predict and get comfortable? A removable discontinuity is when identical factors reduce out of the numerator and denominator. Those identical factors would produce a removable discontinuity where that point is missing as an open circle. A jump discontinuity happens in a piecewise function and that happens when the left-hand limit doesn't equal the right-hand limit. So that approaching any a from the left doesn't end up being equal to any a from the right. And you can most often tell that with a piecewise function. And then an infinite is when you have factors remaining in the denominator. So they haven't been reduced out like in part A in the removable. They're still left behind, and those make an asymptote. And that's when you're going to have an infinite. A vertical asymptote, I should specify. So making not an asymptote, but a vertical asymptote. Okay, so a quick little sample of each of those if you have some room. So maybe x plus 5 over x minus 3 over x plus 4, x plus 5. Right, in that case, the x plus 5s would reduce away, and so we'll have a removable discontinuity at x is 5. There's a remaining factor that didn't reduce in the denominator, and so we would have infinite at x is negative 4. So there'll be a vertical asymptote at negative 4. The x minus 3 doesn't produce any kind of discontinuity. All right, so what kind of discontinuities does f of x have? So let's get this completely in its factored form. X squared minus 9 is the difference of squares. So that would factor into x minus 3, x plus 3, And then you still have the numerator x factor x minus 5. The denominator had x minus 2 in it. And then we've got this polynomial that also factors. And that will factor into x minus 5, x plus 3. So I notice I've got some identical factors which will reduce out from the numerator and the denominator. The first identical factor is x minus 5, x minus 5. So that tells me that I have a removable discontinuity at x is 5. The second I notice is I have my x minus 3. Or x plus 3, I mean. So that will tell me I have a removable also discontinuity at x is negative 3. I have x minus 2 left in my denominator. So that tells me I have a vertical asymptote, or let's say it's an infinite discontinuity. At x is 2. And remember, the x minus 3 doesn't really tell us anything about a discontinuity. But now I could graph this if I knew something about the limits. So now I want to find the limit at all three of these discontinuous places. So I'm going to find the limit as x approaches 5 of the function. And what's left of the function is x minus 3 over x minus 2. That's all that's left. That's this part of it here. So I'm going to plug 5 in. 5 minus 3, 5 minus 2. That gives me 2 over 3. That means on my graph, I am going to draw a hole, a removable hole, at the point 5, 2/3. 5 is the x value, 2/3 would be the y value. So as I sketch this, I'm going to go out to 1, 2, 3, 4, 5. Here's 1, and so 2/3 would be about right here, and I will have a hole right there at that value. Let's do the same thing for the other removable discontinuity. I'm going to take what's the limit as x approaches negative 3, again of what's left of the function. So I'm going to plug negative 3 in. That's negative 3 minus negative 3 over negative 3 minus 2. That's negative 6 over negative 5, or positive 6/5. That means on the graph, my other removable discontinuity would be at negative 3 and then 6/5. So here's negative 3, and then 6/5 is slightly above 1, so I'm going to have another removable discontinuity. What about the asymptote? The asymptote is happening at 2. So that means I need to check the behavior on the left and the right side. So I need to do the limit as x approaches 2 from the left, and I need to do the limit as x approaches 2 from the right. Okay, we know we're going to have an asymptote at 2. So I'll just go ahead and get that right on here. Again, we use what's left. So we'll have x minus 3 over x minus 2. So that would give me 2 minus minus 3 over 2 minus minus 2. That would give me negative 1 minus over 0 minus. Now with zeros, that's where it's important that you do list the pluses, the left and the right still. Okay, because that's the only way to tell what kind of infinity you're going to have. On the top I have a negative number. Negative 1 minus is a negative number, but on the bottom I also have a negative number, because 0 minus is a negative number. That means I have positive infinity. So my graph on 2 minus, or the left side, is going to be going towards positive infinity. So I'm going to put an arrow there because I'm heading on the left side to positive infinity. What about the right side? So I use x minus 3 over x minus 2. I have 2 plus minus 3, and I have 2 plus minus 2. That's going to give me negative 1 plus over 0 plus. Negative 1 plus is still a negative number, but 0 plus is a positive number. A negative divided by a positive is negative infinity. So that means on the left side of the asymptote, I have going towards negative infinity. And then we connect the dots. So I'm going to come up, go around the removable, and then head up to positive infinity. I'll put the arrow on the end. And then for my other one, I'm going to come up and avoid the removable, and I'll head out in that direction. And so that would be a sketch of that graph using all of the pieces of the discontinuity that it has. And that wraps up chapter 1. So we've done chapter 1, lessons 1, 2, and 3, all about limits. Each lesson learning something new about limits. We'll review for a couple days, and then we'll look at our taking our test next week on Monday.